absolute zero temperature, also known as absolute zero, or in degrees Celsius it is minus 273.15. This we will also discuss today. So thus, we I'm not going to pay much attention to the state of matter, since we discussed that. We know that there are vast differences between gaseous, liquid, and solid state, but in the context of that chaotic activity, we know that in gaseous state, molecules possess just kinetic energy. The interaction between gaseous molecules we can neglect, and the only interaction is via collisions. In case of liquids and solids, molecules possess both kinetic and potential energy. So I'm going to write the equation now, but let me focus your attention on those two words being important: random, disordered, ceaseless motion. Motion on microscopic level. And there is a comparison between that motion being random and disordered, and ordered motion. Example is given here. Suppose considering speeding bullet, so all molecules are in motion. However, this is ordered motion, having specified direction. And this motion cannot be described in terms of internal energy. So thus, let me write the equation defining internal energy. The symbol for internal energy is EU. So let me just write it, EU. EU, being an energy, is measured as any energy in joules. So would you please allow to observe students, please change your location, since you do not allow the system to work. So let me tell you, next time, 5 minutes and I'll close the door. This is not possible. 10 minutes to wait, and all will to be punished by delayed students. So, internal energy equation, which is the definition. So, symbol for sum of kinetic energy of all the particles inside the object of interest, plus the sum of potential energy of interacting atoms, molecules, nuclei, all the particles inside the object. Just so this is the mathematical definition of internal energy. So just to explain, so this term, to understand that this is a short way of writing sum of many terms, and the number of the terms being added is given here. In general case n, if we don't know what is the exact value, but if we know that there are 5 particles, each of which having a specific kinetic energy, 5 particles, that's why I'm writing 5. So this is a concise way of writing kinetic energy of the first particle plus the kinetic energy of the second particle plus the kinetic, not sum, just to stand corrected, plus the kinetic energy of the second particle. Don't need to write the symbol for the sum, plus the kinetic energy of the second particle, plus kinetic energy of the third particle, plus kinetic energy of the fourth particle, and the last kinetic energy of the fifth particles. So that we've got 5 particles, each of which having kinetic energy. And for not writing all those terms, we can concisely represent this sum in this way. So the subscript I means what? The number of the particle. So, and it varies from the first one to the fifth. So this is the meaning of the short way of writing sum of many terms. So that's internal energy, collective term, which is considered on microscopic scale. So you know that kinetic energy is energy of motion. That's why the first part of the equation here is called motion part related to particles motion. And this second term, potential energy part, is related to structure, to composition, to the state of matter, to the arrangement. That's why I can write shortly structure. So temperature, what is temperature? Temperature is just the motion part of the internal energy. That's why you can write the symbol for temperature being capital T in SI system of units. And the temperature is proportional to the mean kinetic energy. So let me continue a little bit later. Motion part, just in the way written in the equation, is called heat. So thus, heat is exactly the first term in the formula of internal energy. So thus, what is heat? A kind of energy, of internal energy, which is the motion part of internal energy, related to the ability of particles to be in random disordered motion. Since heat is a kind of energy, it also has the same unit as that of energy, joule. Today we will mention another non-SI system units, which is calorie, but it is popular in case of determining energy content of food. This is another thing. And temperature. What is temperature? Since temperature can be measured using different measuring scales, that's why it is related to the way it is measured, and we cannot write here the sign of equality, but I am going to change this as proportionality. The sign of proportionality. Temperature is proportional to the mean kinetic energy. So in case of denoting mean, we write small stroke above the symbol of interest, of discussion. And now I can continue with sign of equality. How to find the mean kinetic energy. This means the motion part, which will be the total kinetic energy divided by the number of particles, and then we will find the mean or the average kinetic energy. That's why I can write here 1 divided by n being the number of particles in the object, and then sum of kinetic energy of all particles in that object. So thus temperature is proportional to the mean kinetic energy. So we will see in the presentation the main scales used, 3 main scales are used. So the Kelvin temperature, or temperature in kelvins, which is one of the base SI units of measure. This we studied. And also it is widely used in scientific literature and in everyday life. Degrees Celsius or centigrade scale is preferable and more widely used in everyday life. So thus three formulas we have written for internal energy, heat, and temperature. 3 ways of defining it. And also, let me write in SI system, the unit of measure is Kelvin. We do not say degrees Kelvin, no. This is not acceptable, just kelvins, degrees Celsius, but kelvins. And in case of degrees Celsius, we write it in this way. So, so you must understand the difference between those 3 main concepts in molecular physics and thermodynamics particularly. So when objects of different temperature, which means of different heat content, are placed in contact, we know that there will be energy transfer from hotter toward colder object. This is spontaneous process which occurs at the expense of what energy? Energy of random disordered motion from hotter toward colder. So, which means that heat is transferred, but heat is a kind of internal energy. So thus, internal energy is transferred. But I want, and this is those who have read the presentation must have known that we may have objects of drastically different internal energy being placed in contact, and we may not observe heat transfer between them. Why? So I will clear some space, since this is important to understand. Since heat is not the entire internal energy, it is not directly proportional to the internal energy. It is a part of internal energy, motion part of internal energy. But the internal energy depends also on the structure. And if we compare, for example, solids and liquids, solids have got less internal energy than some rigid liquids have less internal energy as compared to solids. So thus, if we consider two objects which has one and the same temperature, we say those objects are in thermal equilibrium. Objects having the same temperature are in thermal equilibrium. So, if the temperatures are same, no heat transfer will be observed. No heat transfer will be observed. So we've got object 1 having temperature T1 and object 2 having temperature T2. If they are same, no heat transfer, depending on the structure of the object. In this case, we may have internal energy of the first being bigger then the internal. We may have different situations. U1 may be bigger than U2. It may be less than U2. This doesn't matter in relation to the heat transfer. Heat transfer is observed only if there is a temperature gradient. Let me introduce that term gradient, but in the context of temperature. So if the temperatures are not same, then heat will be transferred. So which means that heat won't be zero. We will have heat transfer. Heat will be transferred from what? From body of higher toward body of less temperature. From high to less, to low. From high to low temperature object. So this is very important. Just heat is transferred, and the transfer depends on the existence of temperature gradient. So the absolute value of internal energy doesn't matter in this case of heat transfer. So let us see some of the text, and especially there is an example regarding terms hot and cold, which are subjective terms, which are based on our on the way we perceive temperature, and let us just explain many things, which this one, which we can find in verbal way. So hot and cold terms, relative terms, but sometimes they can be deceptive because they depend on the way we perceive the situation of our senses. So that's what is the experiment here? We take two rigid objects, a block of metal and a block of wood. And if initially they both are immersed in boiling water, which means that they will came on at the same temperature, the boiling temperature. When touching them, we will perceive them differently. So the metal block would seem hotter, irrespective of the fact that they have come at the same temperature, because the way we perceive this depends also on one more thing, the so-called coefficient of thermal conductivity, the way the heat is transferred from one object to another. This is given in a law of Fourier, which we will not study today in future lectures. But the law is very much similar to Fick's law, but relating heat transfer. But why not to write it now? Let us write it now. And in this way to revise Fick's law and compare Fick's law and Fourier's law. So let me switch on the board once again. And initially, let me write Fick's law. Fick's law is about what? Matter transfer. The rate of mass or of matter transfer. We wrote it in different ways, in terms of flux, in terms of rate. Let me write both things. So that's why I'll start with J. Let me term it M being flux of matter. So flux of matter. We've got definition for the flux of matter being the amount of mass being transferred per unit time, per unit area, and this is proportional to the concentration gradient. The formula is familiar to you. This is called Fick's law for diffusion. So let me now write the flux of heat. So matter is transferred, but heat also can be transferred. So thus, in this case, I'm going to write the subscript Q because heat is transferred. And here we'll write the amount of heat being transferred per unit time, per unit area is proportional to the temperature gradient. See the analogy between the laws. In both cases, we've got flux. So in both cases, flux is defined. In both cases, the flux is due to what force? Gradient. In case of flux of matter, concentration gradient. In case of flux of heat, temperature gradient. In both cases, we've got sign minus in the equations, which tells us that processes, both they are spontaneous, which means that in both cases, the process occurs from something which is high to something which is less, from high concentration to low concentration in case of Fick's law, from high temperature to low temperature in case of Fourier's law. But how faster this transfer is observed depends on the coefficients of proportionality. So in case of Fourier's law, that coefficient is called the coefficient of thermal conductivity, which tells us how rapidly the transfer will occur. That's why if we touch hot metal, it will seem to us hotter as compared to wood block, because the rate at which heat is transferred from metal to our finger is bigger. That's why terms hot and cold are deceptive, relative, useful, but deceptive. So let us proceed. This we discuss what is temperature, not going to repeat this. Thermal equilibrium also we discussed. When will two objects be in thermal equilibrium if they have one and the same temperature? This we discussed. This also we discussed that the lower temperature object could have the larger internal energy. Why? Because of the structure, because of the potential energy term. So the absolute amount of internal energy does not tell us what would be the direction of heat transfer. Temperature scales, I have mentioned them. Here, it is important to state that fact. For getting reproducible measurement of temperature, it is necessary the device used to measure it to be calibrated. So, for calibration purposes, 2 points reference are needed. They are given in the slide. 2 reference standard points. What are they? Freezing point and boiling point. So, what is the value? So, both points are temperatures at which phase transition occurs. In case of freezing points, so there is phase transition between what? Between solid and liquid. In case of boiling point, so there is a transition between liquid and vapor or gaseous state. What is to be known regarding the difference between 2 reference standard points, which really are temperatures at which phase transition occurs? The boiling point, since gaseous phase is involved here, boiling point depends on pressure, depends on atmospheric pressure. The freezing point not. So that's why always when boiling temperature is given, there needs to be added the value of the pressure at which the transition occurs. And usually, boiling point or boiling temperature is given at standard atmospheric pressure. What is standard atmospheric pressure? This you must have studied at your laboratory topics. So standard atmospheric pressure, the pressure at sea level. So it is also called physical atmosphere. let me switch on the presentation, physical atmosphere. So one physical atmosphere, to change color, one physical atmosphere, ATM, is 760 millimeters of mercury, or this we used when we discussed pressure and circulatory system, and when we transferred blood volume flow rate from liter per minute into cubic meter per second. So thus we've got 760 millimeters of mercury, or 1.01 times. So let me free some space. We've got times 10 power 5 pascals, or since kilopascal is 10 power 3 pascals, this can be written as approximately, there are more numbers here, 101 kilopascals. This is what standard pressure known as one physical atmosphere, and pressure at which usually the boiling temperature is defined. So let me once again switch on the presentation and continue with different scales being used to measure temperature. So we've got Fahrenheit scale, we've got Celsius and Kelvin. So Fahrenheit is less popular now and rarely used. In scientific literature, Kelvin. In everyday life, more popular is centigrade of Celsius scale. Why centigrade? Because that distance between the freezing and boiling point, if it is divided by 100 parts, cents, then this will give the size of a division. That's why centigrade. Each division has got size which is 100 of that distance between 0 and 100 degrees Celsius. So pay attention that there is absolutely same situation in case of Kelvin scale. So the freezing and boiling point, so we've got 100 divisions. So the size of both scales is same. So the main similarity. Also, you see that 0 kelvins, 0 degrees Celsius is 273 Kelvin, since 0 Kelvin is minus 273.15. So this number degrees Celsius. That's why an easy way to change from one scale into another is using exactly that numerical value. So let us proceed with the law first. Law of thermodynamics. It's not discussed in the presentation, but I think that it's useful to tell you that in thermodynamics, 3 main types of thermodynamic systems are introduced. What are they? We've got isolated system, which system does not communicate in any way with the surroundings, which means that nothing can cross the boundary of that system. No energy in neither way. Neither heat nor work can pass, nor matter can pass the boundary. This is isolated system. In case of closed system, energy can pass through the boundary, but matter cannot. And energy can be transferred in two ways. I have already stated this. What are they? In terms of heat transfer and in terms of work performance. Two ways of energy transfer across the boundary of thermodynamic systems. And the third type of system is open system. Living systems from the point of view of thermodynamics are open systems. They exchange with the surroundings heat, work, and mass. All possible forms of energy can be exchanged between them and the environment. So that's why when discussing first law of thermodynamics, we need obligatory to state the system for which the law is defined. Since any of those systems can, for any of them can be introduced first law, but it will be differently quantified and verbally stated. So thus, first law of thermodynamics shortly is a law of conservation of energy. So it is based on the principle of conservation of energy. What is this main principle in physics? The principle of conservation of energy. It says that energy can neither be created nor destroyed, but energy can be changed or transferred from one form into another. So thus, first law is based on that principle. So in case of isolated system, you're not trying to define first law there. Isolated system cannot communicate in any way with the surroundings, which means that its own energy cannot change because no energy can enter or leave the system. So that's why first law of thermodynamics. So I'm going to clear everything and to write the first law now. Okay, so I'm going to write now. So internal energy in case of isolated system does not change. This is the verbal definition of the first law of thermodynamics. So isolated system. Isolated system. How to write mathematically that energy does not change. Internal is meant, of course, here. How to write it? So we write delta being symbol for the change. Change in internal energy. If it is not change, if there's no change, then the change is zero. So, but we know that delta U is what? The difference between the internal energy in final and initial state, and is zero. And then this means that internal energy of the final is the same as of the initial state, or we can shortly write internal energy is fixed, stays same, or is constant. Constant meaning something which is fixed and does not change. So first law of thermodynamics for isolated system. In case of closed system, we write first law in this way. Internal energy may change if there is heat transfer or work performance between, or as a result of interaction between the system and surroundings. So, verbal definition, internal energy may change if heat is transferred or work performed. So the formula contains the so-called, the specific convention regarding signs of the quantities being included in that equation. So thus, delta U can be either positive or negative, Q can be either positive or negative, W as well. So let us discuss exactly this. Since if you write the law in this way, or if you write the law in this way, it's possible. Everything depends on the specific transfer or specific way the work is performed. So let us begin with initially delta U. So thus delta U can be either positive or negative. So being positive, having in mind the way of defining delta U, this means that U1 minus U2 minus U1 is positive, which means that U2 is bigger than U1, which means what? That the internal energy of final state is bigger than of the initial state, which means what? That internal energy increases. So you may say internal energy increases or delta U is positive, which is exactly one and the same. Absolutely in the same way, which means that internal energy decreases in the second case. So internal energy decreases or delta U is negative. So students in the exam may state internal energy is positive or is negative. Internal energy is always positive. We are discussing change in internal energy, so which is not the same. Since we know what is internal energy, sum of kinetic and potential energy of all the particles inside the object. So that if a student say internal energy is negative, this means that she doesn't have any idea about the theory and the law. Regarding heat, here we've got convention. Heat or work, they are defined in what way? The rule is, if as a result of the process, heat transfer or work performance, internal energy increases, then it is to be considered, or they must be considered positive. Specifically, for heat, when will heat transfer increase the internal energy of the system. If heat is added to that system, if it is absorbed by the system, so thus heat is positive if it is added. It is negative if it is released. Since if a system releases heat, its internal energy will decrease. What about work? Absolutely the same. If work is performed in a way to increase the internal energy of the system, it must be considered positive, which means that if work is performed by the external bodies on the system, then it must be considered positive. So W is positive if it is performed on the system. It is negative if work is performed by the system against the external object. So by the system against the external objects. So this is the convention regarding heat, work, and internal energy changes. So we'll see the presentation, and then we'll come back to explain isothermal expansion, which is an important phenomenon. So, internal energy, there were some examples here. Internal energy may change, so I'm telling this many times. So may change if there is heat transfer or work performance. So suppose internal energy changes, suppose it increases. We cannot say what makes this change to occur via heat transfer or work performance, and example is given here. So we've got some volume of gas at 20 degrees Celsius, and suppose this gas is compressed, which means that work is performed on the gas to that final volume, and the temperature increases. So this is the final state. Final internal energy depends on the final volume and temperature. The same situation can be achieved in another way. We've got same volume but lower temperature, and if we put the gas container over flame, then if we heat it, then we may reach a situation in which the internal energy is same, 40 degrees Celsius and 200 cubic centimeters of volume. So that the value of internal energy itself does not tell us what is the process which produced that change and that value of internal energy. So I mentioned, so C, it is given that term in red, isothermal expansion of a gas. What does it mean? Isothermal. So this is the term tells this. So we've got no change in the temperature of the gas, no change in the temperature, although there is heat transfer and work performance. When will this occur? So let me, not given picture, not given picture, but let me draw or sketch a picture. We've got, to clear everything, isothermal expansion. Let me write in general, the first law of thermodynamics for a closed system. Suppose there is a container, we've got gas inside, there is a piston. Suppose heat is added to the gas, which means that heat is positive, which means that the internal energy of the gas will increase, thus allowing it to expand. Expand means to push the piston upward. So, which means that the gas will perform a work. So this is the new piston location, which means that we know that work is force times displacement. Since gas performs work against the surroundings, the work is negative according to the convention. And if the amount of heat being added, so those vertical lines means magnitude is discussed here, not sign. If the amount of heat is exactly equal to the work performed, so in magnitude, those different forms of energies are same, then we've got two terms, first positive, second negative, being of the same magnitude. They will not produce change in internal energy, and the temperature of the gas will stay same. And you may be asked, is it possible to add energy to a system? Is it possible the system to perform work and the temperature of that system to stay same? Yes, this is a situation in which this can occur, but we need to have equal amounts of energy transfer in both directions for the net change to be zero. So this is isothermal expansion. And now, let us discuss a phenomena which is called thermal expansion. Thermal expansion, which means what? Changes in the original size of objects as a result of temperature change, as a result of heat transfer. So, solids occupy the central part here. Suppose solids absorb heat. As a result of this heat addition, the heat is of motion part of the internal energy. This means that if heat is added, the particles will move more intensively, more agitated, will be the internal particle motion, and as given here, they will, in case of solids, atoms cannot move freely as in gaseous state, but nevertheless, they are in constant motion in the form of vibrations about equilibrium position. That's why these vibrations would be more intensive and they will vibrate over greater distances, which results in the so-called photographic enlargement. So linear change in dimensions in all directions. That's why we can introduce three types of thermal expansion: linear, area, and volume expansion. It is not given here, just linear expansion is given. If just the length of some bar or of some object having just one dimension changes. So thus, let me write the law, which by and by you can see here, just for the linear expansion. So let me write the three laws here regarding expansion. So suppose the length of the object of interest is L. Suppose its original length is L. And as a result of addition of heat, the length, suppose, has changed by some amount. Let me denote it by delta L. So thus, we've got delta L being the change in the length, final minus initial length, over the original one, initial one. This is called fractional expansion. Fractional expansion. Fractional expansion, in case of considering the process in one dimension only, is proportional to the change in temperature. So let us change the symbol. I think the symbol alpha was used, the Greek letter. That's why let me change the symbol from K to alpha. Alpha being the most popular coefficient of thermal expansion. This is the name of this Greek letter alpha. So that fractional expansion is directly proportional to the temperature change. However, if there is change in two dimensions, then area, some area changes. We can write similar equation, but since there are two dimensions, twice alpha delta T. Oh, in case of volume, we've got three dimensions, which is called volume fractional expansion. And it is 3 times alpha delta T. So linear area and volume expansion. The coefficient of expansion, thermal expansion, has got unit of measure, which we can find if we solve the equation in relation to alpha. So thus, unit of measure. If it is length, even if it is change in the length, unit is in meter, length in meter, change in temperature in kelvins. So thus, it is Kelvin power -1 or degrees Celsius power -1, depending on the way the temperature is expressed. So this is about the laws of expansion, or even Fahrenheit is given here. If temperature is measured in Fahrenheit, why not? So that phenomena of thermal expansion is of importance regarding what the phenomena such as if some glass object is placed over hot surface, it may break. Why? Because the lower part of that object expands differently as compared to the upper side. Also, in case of dentistry, in case of some, which is given example, mercury, silver, amalgams. So materials must have one and the same coefficient of thermal expansion to prevent formation of destructive stresses, which will, of course, have a bad effect on the tools. Exposed to this temperature gradient, you know that OM may consume either cold or hot food. So